Welcome back. And we were discussing the effect of feedback in the performances of our circuit. What we have discussed in the previous class was the fact that thanks to the feedback, we may finely tune the transfer function of our system in a much more precise way with respect to what we have with an open loop configuration. Another interesting aspect is in the fact that thanks to feedback, we may somehow reduce the effect of nonlinearities in the amplification stages of our circuit. This is precisely what is discussed in this slide, which I have reported here on OneNote to better analyze the different passages. So the idea is that in generic configuration, feedback configuration, we have a situation like this. So the input signal enter a mixing circuit in which the signal coming from the feedback loop is subtracted. Then we have the amplifying stage. Let's say in an ideal configuration, we have that we are just amplifying linearly the difference between the input signal and the signal coming from the feedback. Okay, so this is, let's say, the ideal situation. In this ideal situation, we have that V out over V in, that is the transfer function of our system, is given by the gain, the linear gain that we have in the direct loop, divided by 1 plus A1 times F. Okay, so if this term is much larger than the unity, this relationship can be approximated as 1 over F. Okay. Well, actually, we can derive also some other relationship starting from this one. For example, we can say that if we move this Vi here and A1 on the other side of the equation, we have that V out over A1 is equal to V input divided by 1 plus A1 times F. Okay, so this is simply moving Vi here and A1 here. Another interesting aspect is related to the fact that if we look at V out here, then here we have V out over A1. And V out over A1 is also given by Vi minus F times V out. So we can also say that V out over A1 is both equal to this quantity here and to this one. Okay, so we can say in the end that Vi minus F V out is equal to Vi over 1 plus A1 times F. Okay? So this is indeed true for a configuration in which we do not have nonlinear effect, but suppose that we are now in a situation in which indeed we have also nonlinear term for them, for example, a third order term here in the amplification stage. You must imagine that here we have an operational amplifier or in an inverting or non-inverting configuration or something like this. Okay, so the operational amplifier is not indeed perfectly linear, but we will have to some extent also some nonlinear effect. For example, in this case, we are modeling a third order function. So in this case, V out is equal to A1, which multiplies VI minus F V out, plus an additional term, which is A3 as coefficient, time, again, VI minus F V out to the third power. Okay. Then we can apply this rule here to this term, which is the linear one, to rewrite the initial equation in the following way. So V out, which multiplies 1 plus A1 times F is equal to A1 times VI, because we moved this term, I mean part of this term in the left-hand branch, plus the effect of A3 time VI minus FVO to the third power. Okay, so basically we are exploiting this relationship and plugging in here. Okay, so if we do so, what we have is that we can rearrange this expression again by exploiting this relationship here. That is, we have that V out 1 plus A1 times F should be equal to A1 times VI plus A3, and rather than having this term to the third power, we plug this guy here to the third power. So A3 VI to the third power divided by 1 plus A1 times F, again to the third power. Some other manipulation is needed. So again, I'm moving this term back here. So what we have is that V out is equal to A1 times VI over 1 plus A1 times F. And this is A3 times VI to the third power divided by 1 plus A1 F to the fourth power, because we are dividing this term times this one. So the bottom line is that if we look at the relationship between V out and VI, sorry, just 1 second. We have some technical difficulties here. Okay. So the bottom line is that indeed we have third order effect related to VI in the output, but these third order effects are multiplied by a coefficient which we can call let's say B3, and this is B1, and clearly B3 is much smaller than B1 because we have a denominator in which we have A1 times F raised to the fourth power. Okay, so basically we indeed achieve a sort of desensitization of the nonlinearity in our circuit. Okay, this is what happens, for example, if we have a configuration with indeed A1 and A3, and some kind of differences in the actual slope generated by the open loop. After the usage of the negative feedback, somehow the nonlinearities that we have are attenuated. Okay, in the sense that the new slope is closer to linearity with respect to the old case. Okay, without feedback. Okay, this is important for distortion reduction. Another interesting benefit of negative feedback is the minimization of the impact of possible interferences applied to our circuit. So, for example, here you have a situation in which we have a direct amplification of the signal. If the signal is somehow corrupted by noise, then the signal-to-noise ratio that we have at the output is just the same that we have here. So in terms of the relationship between the Vs and Vn value. What happens if we do have feedback? So let me resketch the previous circuit. So the first configuration is based on a certain source voltage corrupted by a noise or interference source here, and then we have the amplification. The signal-to-noise ratio can be estimated at the input, and this is the relationship between the signal value with respect to the noise value. But if we look at the signal-to-noise ratio at the output, we have that we do have the same relationship between noise and the signal component, because signal is amplified by a factor which is equal to the gain of the amplifier, and the noise as well is multiplied by the same effect. So there is no benefit in the amplification of the signal in this case. But the situation may be radically different if we have a configuration like this. So certain signal component, then the given feedback loop, which acts by multiplying according to a factor beta the differential input that we have here. Then we have some initial low noise amplification stage A2. Then we have at a certain point the interference that we experienced before. Then we have another stage which is A1. Okay, and this is the output. And this differential signal is then connected to the feedback loop. Okay, so in this case, V out is given by, let's say, the output associated to the signal Vs is associated to the input signal Vs time the chain of the two amplifying stages, so A2 time A1, this is the gain of the direct loop, divided by 1 plus beta time A2 time A1. Okay, this is the conventional expression for feedback loops. What about the output related to Vn? Well, the output related to Vn is Vn, which is multiplied by the direct loop, which in this case is A1, and it is divided by the feedback effect. So we have the characteristic equation, we have the factor beta, A2, and then A1. Okay, so basically in this new loop, this is F, okay, what we have called F, the feedback loop effect with respect to the interference. So if we compare these two quantities, what we have is that in the first case, the amplification factor is substantially 1 over beta if we assume that this quantity here is much larger than the unity. And in the second case, the amplification factor is 1 over beta times A2. Okay, so the bottom line is that the signal to noise ratio at the output is Vs time 1 over beta divided by V noise time 1 over beta time A2. Okay, and this is good news because this means that with respect to the original signal to noise ratio, which was Vs over Vn, now we have, well, this 1 over beta factor can be simplified, but we can say that the signal to noise ratio at the output is Vs time over Vn time A2. Okay, so we have this amplification of the signal to noise ratio. Which is indeed highly beneficial. Another interesting benefit of negative feedback is given in terms of output and input impedances modification. So, for example, if we have a configuration like this, with the basic amplifier, which is characterized by a given input impedance Z sub I. And then we can model the output port as the effect of the amplification according to the factor A with respect to the input voltage VE. And then we will have a certain output impedance associated to the amplifying stage. So then we plug this circuit into a feedback loop. So we take this signal and this one, and we use it in a feedback network which takes as input V out and generates an amplification of V out according to the factor F, which can be even smaller than the unity. So this is VI, so VE is VI minus F V out, okay? So let's see what happens in this case. So V out is basically VE times A. If here we have an open circuit, no current can flow in this branch, and so no voltage drop occurs over ZO. Well, VI is equal to, indeed, VE plus FVO. And therefore, we can replace VO with this quantity here and say that VI is equal to VE plus F times A times VE. So bottom line is VE is equal to VE times 1 plus FA. The input current here, I sub I, is basically VE over the input impedance. Okay, the current which is flowing in this branch can be estimated from the ohm law. Okay, is this okay with you? So now we can compute VI over II, so the input impedance of the whole circuit, as this quantity divided by this one. Okay, so we can easily check the fact that the new input impedance is the original one of the pure amplifying stage, so little z sub I, times 1 plus F times A. Okay, this is quite interesting because this implies that the new impedance achieved with the feedback loop, the input impedance is much higher than the original one. And typically, when we want to amplify voltage signals, this is good news, because we don't want the input signal to be wasted over the parasitic source of resistance. Okay, so the idea is that the higher is the input impedance, the better, because in this case we have a voltage divider effect which is negligible. Okay, if Z sub I is very large. Okay, because the VI is Z sub I over Z sub I plus RS, the input, the parasitic impedance associated to the source. We wanted this quantity to be as close to the unity as possible. Okay. Another interesting aspect is related to the output impedance. The output impedance is, the global effect due to the input voltage. Then we have indeed the output impedance, and then here you may have given load resistor or load impedance. In this case, again, we want the actual output to be as close as possible to the gain generated at this point. So this actually would be A times VI times RL over RL plus Z out. Okay, so it is important to have a very small Z out. Okay, we want this quantity to be very small because we don't want this ratio to be far from the unity. Well, you can get back to this circuit. And what you can do is to estimate the ratio between V out and I out. So now you have to assume that there is a certain current here. But you have to do so considering a null input, okay? Because D out is typically computed when as the ratio between V out and I out when the input voltage is equal to 0. Okay. Well, if you go through the circuit and you compute V out under these circumstances, you have that V out is equal to A times VE times the current plus, sorry, the current I out times Z out, little Z out. Okay, so let me get back here. So now we indeed do have a voltage drop over Z out because we are not considering the circuit in open condition. Let's say RL equal to infinity. So there is some current flowing here. And when we do have some current, V out is given by A times VE plus the voltage drop over Z null. Concerning VE, we do have that VE is linked to VI on the basis of this formula, but VI is null when we compute the output impedance. Okay, so we can simplify this formula and say that V out minus A times VE is equal to I null divided by Z out. So this is just a rearrangement of this equation. Another important fact is that, as I said before, VE plus F V out is equal to 0, and this is due to the to this relationship here. Okay, when V input is equal to 0. So last passage, we can use this formula to plug V out here. So we have that V out minus A. So let me first rearrange this one. So VE is minus FV out. So if we plug this result in here, we have that V out plus AF V out over Z small z null is equal to I out. Again, some algebraic manipulation. So V out times 1 plus AF is equal to I out times Z out. And finally, we have that V out over I out, which is our output impedance, capital Z sub null, is equal to Z out over 1 plus A times F. Okay, so the output impedance of the whole circuit is the output impedance of the amplifying stage divided by this quantity. So since typically this denominator here is much larger than the unity, we have that the output impedance after the application of the feedback loop is much smaller than the output impedance of the pure stage. Okay, and again, this is good news. So so we are in a very favorable situation thanks to the feedback loop, because the input impedance is increased by this factor and the output impedance is decreased by the same factor. Okay, so a lot of benefits are originated by the connection through the negative feedback. So let me get back to the study material, where you will find these schemes. So we have discussed the reduction of the interference, and we have discussed the optimization of the input and output impedances, which are generated by the feedback loop. Let me further introduce the benefits of the negative feedback. For example, the effect related to bandwidth. Okay, so let's suppose that our amplifier is characterized by this single order function, okay, transfer function. This is in the Laplace domain, so you must imagine that this S can be converted into J omega. So basically, this is a single pole transfer function. Okay, so the effect is something like this. Okay, after P1, we have a degradation of the initial DC value of the amplification, and this degradation goes as minus 20 dB per decade. Okay, And so after P1, indeed, we do have this degradation. What happens if we apply the feedback loop? Well, you must remember that whenever we have a feedback loop, the gain of the stage of the amplifying stage is divided times this characteristic formula 1 plus A of S times F. Okay, this is the formula that we have already analyzed and applied several times. Okay, so if you replace this A of S with this formula, with this first order transfer function, what you get is this global formula here. So from this formula, it is evident that the DC gain is changed as expected. Okay, the DC gain change is the one that we have discussed so far multiple times. So A0 divided by 1 plus A0 times F. If this is much larger than the unity, we can say that this quantity is more or less 1 over F. What about the frequency behavior? Well, frequency behavior is controlled by these this part of the transfer function, and in particular by the relationship between the old pole positioning and this new effect. Okay, the multiplication of the pole position times 1 plus A0 times F. Once again, this is a very large quantity, so this means that we are moving the cutoff frequency at higher values, okay? And in particular, the multiplication factor for the pole, P1, is multiplied by this term, 1 plus A times F, which is the same quantity, let's say A0 times F, which is the same quantity which is applied at the denominator of the amplification. Okay, so basically we get a reduction of the gain of the pure amplifier in terms of the DC gain by a factor which is 1 plus A null times F, but the same quantity multiplies the pole. So the idea is that in the logarithmic plot, we have a reduction of the gain, but this reduction is compensated by an enlargement of the bandwidth. And basically, the reduction in the gain is totally equivalent to the increment in the bandwidth. Okay. So since here we have a minus 20 dB per decade curve, we are moving along this curve the corner here, okay? Minus 20 dB per decade, which means a reduction of a factor of 10 every increment of 10 in the frequency domain. So in the bilogarithmic plot, the hyperbolic relationship between gain and frequency turn into a linear relationship. Okay, so bandwidth is increased by this factor, and the DC gain is decreased by this factor, but typically this is not an issue because we don't want arbitrarily high gain, we want precise gains controlled by this factor here, 1 over F. Okay, so this is a graphical representation more accurate with respect to what we have seen in the what I have sketched in the previous slide. So you see that this black curve is the original curve for the direct path gain. After the addition of the feedback loop, we get the red curve. Okay, the red curve is the asymptotic plot. So reduction of the DC gain by a factor which is 1 plus this T null, T being T null is this quantity here. And the same 1 plus T null factor is used also to enlarge the bandwidth of our circuit. So bandwidth increases by 1 plus T null, gain is reduced by the same factor. The same concept illustrated in this plot can be seen as a shift in the pole positioning in the complex plane. Okay, so the new pole is 1 plus T null P1, and it is therefore much further apart from the origin. Okay. Let's sum up the benefits of negative feedback. So we have discussed the fact that through negative feedback we can achieve a precise gain definition of our circuit, gain desensitization, which means that even if the gain of the amplifying stage changes by a factor, let's say A1 plus delta A, this amplification is somehow negligible because of the feedback loop itself. The feedback contributes also to the nonlinearity reduction, which is again good news. We may get a reduction of the impact of the interferences, as we have seen by analyzing the loop. We optimize the input and the output impedance. We can increase the input impedance and decrease the output impedance, which is very good for voltage amplifications. You can also use feedback to achieve the opposite effect, which when you want to amplify currents, because in that case you want a very low input impedance and a very high output impedance. Another interesting effect is the bandwidth enlargement. So feedback is beneficial also in this sense. Unfortunately, as usual in the electronics domain, there are also some undesired effects. One of these is the fact that we may compromise with feedback stability. Okay, we must be much more careful about what is the frequency behavior of our circuit, because after the application of the feedback loop, the risk is having poles with positive real parts. Okay, and having such poles with the positive real part means instability. Okay, let's have a short break, and then after the break we will discuss stabilities, Nyquist criterion for stability, concept you should be already familiar with, but we will review this concept. Okay. Okay, so let's get back to the stability analysis. Okay, the problem, as anticipated, is in the fact that in the new frequency response of the signal, due to the manipulation induced by the feedback loop, we may have different pole positioning. To estimate the pole position, what we should do is to find the roots of this denominator here. In some cases, this can be quite tricky, okay? Because we may have the information related to AS, to FS, but we may not know the effect of this addition of the unit, okay? So we would like to have a fastest method to estimate the stability of the circuit, and this can be done by focusing on these TS, which is the multiplication of AS times F of S, and this can be done by virtue of the so-called Nyquist criterion. So the Nyquist criterion states that the system is unstable if the transfer function related to the multiplication of AS and FS, which is also called the loop gain. So when the loop gain amplitude is larger than unity at the frequency where the phase of the same quantity is minus 180 degrees. So to check this, I mean, to avoid this situation in which the system becomes unstable, we may look at two quantities, namely the phase margin, which is defined as the frequency where the transfer function is equal to 1. I mean, at this frequency, which we will call omega null, we have to check this quantity here, that is the summation of the phase of the loop gain at this specific frequency plus 180 degrees. Or if you want, since typically the phase shift is negative, this phase margin here is basically the difference between the phase curve related to t of j omega, so the phase of this quantity, and the minus 180 degree line computed this quantity specifically at the angular frequency omega null, which is the one which corresponds to the unity of the loop gain. So the difference between this phase curve and the minus 180 degree line is indeed the phase margin. or we can investigate the so-called gain margin. So when the phase margin is positive, indeed we have stability. When, if not, the system may become unstable. The gain margin instead is defined as this ratio here, where omega 180 is the frequency in which the phase is equal to minus 180 degrees. Okay, so if the gain margin is smaller than 1, then we have instability by virtue of the Nyquist criterion. Okay, mostly we will focus on the phase margin analysis because it's more easy to find the unitary gain angular frequency. So the idea is that when we have a generic transfer function for A of S with multiple poles, we can indeed sketch the frequency response associated to this transfer function. So what we can do is to start from A0 in dB, and then sketch an asymptotic plot in which whenever we hit the angular frequency corresponding to a given pole, we have a minus 20 dB per decade decrease in the value of the loop gain amplitude of the direct path gain A of j omega gain. So here we have the solid curve here, here, and here. Okay, so after P1 we start losing 20 dB per decade. After P2 we start losing a minus 40 dB per decade. After P3, minus 60 dB per decade. Similarly, in the phase plot, what we can say is that each pole generates a phase loss equal to minus 90 degrees. Okay, and this is combined for all the poles. So first pole we lose 90 degrees. After the second pole effect, we lose 180 degrees, and so on. What is also typical is that when we have the phase loss associated to a pole, half of it is occurring before the pole position, and so minus 45 degrees before the pole position, and minus 90 degrees after the pole position. Okay, so let's say 1 decade after the pole position, more or less, we have already lost 90 degrees in terms of phase. Okay, some more considerations. So we have discussed the fact that we are interested in analyzing T of S, so the loop gain, so the multiplication of A of S times F. Another important effect is related to the fact that if A null times F is much larger than the unity, we have that the gain at the DC of the amplifier in the feedback loop is more or less equal to 1 over F. Okay, so again, T null is more or less A null times F, okay, which is much larger than the unity. So in dB, A null is equal to 20 logarithm base 10 of 1 over f, okay, with a very good approximation. So suppose that this quantity here in dBs is given by this dashed curve. Okay, so it's interesting to analyze this in the bilogarithmic plot, in particular by representing decibels, because since we wanted to compute this product, AS times F, what we can do is to consider the fact that the separation between this curve and this one in the logarithmic plot is given by, so this jump x is given by this formula here. So 20 logarithm of 10, amplitude of A of j omega, this is this curve here, minus the dashed curve line, which corresponds to this quantity here, minus 20 logarithm base 10 of 1 over f, because 1 over f is a null. Okay? If we apply the let's say, calculus rules, we know that when we subtract two logarithms, we can compute the logarithm of the ratio between the first element and the second one. So A of j omega over 1 over f, which means A of j omega times f. Okay, but this is the loop gain. Okay, so this quantity here is precisely the loop gain, which means that the loop gain can be associated to the A of j omega curve by looking at this difference x. Okay, so the idea is that the quantity tau of j omega in terms of amplitude can be found by considering just this this part here of the plot. So basically, in the t of j omega representation, we have that the old A null level becomes our 0. Okay. These considerations are illustrated also in the next slide. So distance x, so this drop here from the value of A of j omega modulus with respect to A null is the direct measure in decibels of the loop gain magnitude, the absolute value of T of j omega. And what is interesting is also that if you remember to check the Nyquist criterion, what we can do is to find the value of omega, which equates the amplitude of the loop gain to 1. And by looking at this graph, we have that 1 obviously corresponds to 0 dB. Okay, so the 0 dB value of T of j omega is at this point here. Okay, because the difference between the two curves becomes null. This means exactly 0 dB and therefore unity of tau of T of j omega. Okay, so this is again a detail in these notes. So basically, the line corresponding to this quantity here 20 logarithm base 10 of 1 over f is our new 0 dB value. Okay, is the new is the value which corresponds to the amplitude of t of j omega being equal to 1. So if this part here of the plot is basically our t of j omega, and this is the new 0 dB value, then to find the phase margin once again is 180 degrees plus the phase corresponding to the omega 0 dB angular frequency. So this quantity here can be found by looking at the position in which t of j omega is equal to 1, and this is it basically, this one. Okay, in this point the loop gain is equal to 0 dB, and then we have to jump into the phase curve. By the way, the phase curve of A of j omega is equal to the phase curve of A of j omega times f if f is not a function of the angular frequency. Okay, so in this case we as typically is, we can focus on the phase of A of j omega. So in this specific case, A of j omega, as you see, is a single pole function. Okay, we have just a minus 90 degree phase loss in our system. And if we look at the value of the phase at the omega 0 dB angular frequency, we have that the phase is equal to minus 90 degree. So if we perform this computation, what we have is that the phase margin is equal to 90 degree. Okay, 180 minus 90 degree. Or as you see, you can compute the phase margin as the distance of the phase curve with respect to the line at minus 180. Okay, so we have a quite consistent phase margin. 90 degree means clear stability in the behavior of our circuit. Suppose that we wanted to have a phase margin equal to 45 degrees. What does it mean in practice? Well, in practice, this means that the phase curve in correspondence to the loop gain equal to 0 dB must be equal to minus 135 degrees, so that the distance from the minus 180 degree curve is equal to 45. So this is the idea. Okay, so the phase at the null at the 0 dB angular frequency must be equal to minus 135 degrees. Okay, so if taking into account that omega 0 dB is defined as the frequency which generates this equation, so the loop gain equal to unity. This implies that in this specific position of the frequency axis, we have that the gain associated to the direct path is equal to 1 over f, okay? Because A of j omega null times f equal to 1 implies this equation. Okay, if A of j omega null is equal to 1 over f, we can exploit this result in the overall gain expression, in the sense that A of j omega is given by this expression here, so we can plug 1 over f to replace A of j omega. T of j omega is A of j omega times 1 over f, time f, sorry. So if A of j omega is 1 over f, T of j omega is equal to 1, okay? Well, actually, the modulus of this expression is equal to 1, while the phase should be this one because the phase margin is 45 degrees. So we have we can characterize both the modulus and the phase of this quantity, and this corresponds of having a Fourier exponential in which the exponent is indeed the minus j of the phase shift. Okay, so minus j times 135 degrees. Okay, this is actually the definition of a complex number whose amplitude is equal to 1 and the phase is equal to this one. Okay, so if you have a generic complex number, let's call it z. The idea is that z is z modulus times e minus j. Well, e to the j, to, let's say, plus j times the phase of the complex number. Okay, so phase of this particular complex number is minus 135 degrees. The modulus is equal to 1. That's the reason why we have this expression here. What is interesting to observe is that if we compute the modulus of this expression, what we get is this final result here. Okay, so A of j omega in correspondence to the 0 dB angular frequency correspond to this this result here. 1.3 over f. Okay, so basically this is larger, let's say simply larger than 1 over f. So at the angular frequency, which corresponds to loop gain equal to 1, we have a global gain which is larger than the DC gain. So 1.3 times the DC gain. So this is the case for the phase margin equal to 45 degrees. If we consider the case of phase margin being equal to 60 degrees, we have that therefore the phase of the loop gain must be equal to minus 120. And if we follow a similar analysis with respect to what we have seen in the previous slide, we have that the global gain should be equal to 1 over f, which is also the gain at the null frequency. Okay, so there is no gain reduction nor amplification in this case at omega equal to omega null. So omega null, once again, is the angular frequency which generates a modulus of the loop gain equal to 1. Finally, let me discuss the case of phase margin equal to 90 degrees. So in this case, this means that the phase of the loop gain should be minus 90 degree, and if we repeat the same analysis performed for the 40 degrees case in the last one, what we get is that we have a certain reduction of the global gain with respect to the gain at DC, and this reduction is basically coincident with the 70% of the original DC gain, which means more or less a 3 dB loss with respect to the DC gain. Okay, this is what happens in practice. Okay, so with a phase margin equal to 90 degrees, you see the actual value of A of j omega over A null is this one. Is for the 90-degree phase shift. When you have a 60-degree phase shift, you have a very small overshoot, and then you get to the original DC gain when you are in correspondence to omega null. Relative frequency here means omega over omega null, essentially. 45 degree, you see there is this quite pronounced overshoot. With a smaller phase margin, you have an even larger overshoot in the global frequency response. And as you may imagine, when the phase margin is even smaller than that, you will have a very large overshoot. At the end of the day, if the phase margin is null or negative, then you will have such a large overshoot that you will get instability. Okay, again, let me further discuss the concept of phase margin and gain margin. So the idea is that the phase margin indeed is computed when the loop gain is equal to 1. While the gain margin is computed when the phase is equal to minus 180 degrees. Okay, so we may have some different situations. For example, in this case, you see that when we are at gain equal to unity. Loop gain equal to unity in modulus, you see the distance between the phase curve and the minus 180 degree one is relatively small. So we have this quite pronounced overshoot in the frequency response. When we have this overshoot in the frequency domain, this corresponds to step function with a lot of fringing effects. Okay. In the second case, when the gain is equal to unity, we have a quite large distance of the phase curve with respect to the minus 180 degrees. So this second case. In this second case, this such a large distance means no overshoot in the frequency response of the global circuit, and no overshoot means also a relatively smooth increase of the output when we apply the step function as the input. Okay. If you want to further deepen this concept, you can refer to the book of Professor Razali. Okay, so here you see an example in which the circuit is stable. This is due to the fact that the dashed line corresponding to A0, you see, is quite high, okay, at this level. So if we look at omega null is again the angular frequency, which corresponds to a loop gain equal to 0 dB, which is the case in this specific point. So we have to look at the phase at this point, and the phase is here. Since we have a lot of phase margin, because the distance between this point and the minus 180-degree curve is very large, then we do have stability. Okay, we can do the same by looking at the so-called gain margin, but typically, again, I would recommend to focus on the phase margin. Okay. Okay, so in this case, the circuit is stable, but this may not be the case if the value of A0, so the DC gain of the global circuit, again, this is 1/f, changes. Okay, so if we pick up a smaller A null, let's say A1 placed at this point, or A2 placed at this one, well, let's investigate the stability. So to check the stability of this condition here, we have to look at this point, because once again, the distance between the solid black curve is x, and this is equal to the transfer function associated to the loop gain in terms of modulus. So here we get to the point in which t of j omega is null, so we have to check the phase margin at this point. So the phase curve is here, and well, this is, let's say, a very borderline situation, because it is the distance between this point and the minus 180-degree curve is relatively small. So we can say that we meet the Nyquist criterion, but we are at the very limit of it. So if we further reduce the DC gain, we may get in trouble, in the sense that for the second configuration, the loop gain is null in this specific point, and this specific point means that the phase curve is below the minus 180-degree curve, and therefore the phase margin is negative. In this case, we won't have stability. So an important effect, as you may see, is that the more we reduce this quantity, 1/f, the greater is the risk of having the circuit unstable. Okay, and typically f is a passive, is the transfer function which results from a passive circuit, which means that f cannot be larger than 1. Okay, so if 1/f should be larger to get the stability, the problem is the minimum value that 1/f can reach. And so if f is mandatorily smaller or equal to 1, then 1/f has the smallest value when f is equal to 1. Okay, so if f is equal to 1, we have the most difficult case to compensate. Okay, because f equal to 1 means so substantially having a curve at this point, where A null is equal to 0 dB. Okay? So to investigate the stability of an op-amp, let's say, when connected in a feedback loop, what we can do is to place the op-amp in the most complex situation to be 100% sure that in every other circumstance we will have stability. And indeed, the most complex situation for stability is this one, because this one means unitary transfer function for feedback loop, and therefore this could be very difficult to achieve stability. The next slide, you see what can be the stability, the effect of the phase margin in terms of the step response. So step response equal to this ringing effect when we have a phase margin equal to 45 degrees, a much smoother step response when we have a phase margin equal to 60 degrees, and even smoother step response when the phase margin is equal to 90 degrees. You may see that phase margin equal to 60 degrees is a very good compromise, because a phase margin equal to 90 degrees has a relatively small slope, while the reaching of the final value, stable value, is much more rapid with a phase margin equals to 60 degrees. And at the same time, 60 degrees implies no oscillation at all. Okay, so of course we need a phase margin larger than 0 to achieve stability, but we must take into account also the fact that in some cases we may want much larger phase margin to get no oscillations in the circuit behavior. Okay, let me go further in this analysis and to discuss the problem of frequency compensation. So we have said that in some cases, if we have, for example, a circuit like this, and we have a feedback loop with a feedback value like this one, so relatively high, and consequently we generate an A null low, we may have indeed a negative phase margin and therefore instability. So how can we cope with this problem and avoid this effect? But what we can do is to transform the frequency response of the amplifying stage so that when put in the feedback loop, the phase margin is still positive. So there are some techniques to implement this concept. One way to proceed is to apply the frequency compensation by means of the addition of a new pole, a new dominant pole. This technique is also called narrow banding. How does it work in practice? So let's suppose that we have the necessity to achieve a stability with a unitary feedback loop. Okay, so the most complex situation. Suppose that the initial gain of our amplifier is provided by the black solid curve. This one. You see the transfer function associated to this A of j omega has 3 poles. And each pole induces a phase shift equal to 90 degrees. So the bottom line is that in the initial situation, corresponding once again to the black solid curve, the phase margin should be computed here, because this is the angular frequency which corresponds to a null loop gain, a unitary loop gain, sorry. So we have to jump to the phase curve. So we get this phase shift, which is larger than the 180 degree phase shift. So this means that the phase margin in this case is negative. How can we cope with this problem? Well, the idea is to deliberately add a dominant pole to our circuit. We will see some circuit technique to implement this idea. So we had this PD, this dominant pole, and by this addition, this means that the A of j omega curve is modified, in the sense that we have now this the behavior highlighted by the dashed curve, in the sense that after the dominant pole we start losing 6 dB per octave, or if you want 20 dB per decade. Okay, so this means that after the addition of this dominant pole, we hit the f equal to 1 curve at this new point corresponding to the old P1. Okay, so the new phase curve is the dashed one. So because of the presence of PD, we have a 90 degree phase shift induced by PD. So we have this initial phase shift here. Then we start to experience the influence of P1, but luckily, when we get to the new omega null, we have the phase curve, which is at minus 135 degrees, which means that the new phase margin is equal to 45 degrees. Okay, so the circuit after the addition of the dominant pole is indeed stable. Okay, the phase margin is positive. Okay, so this is very important. We have gained the possibility of having a stable circuit, but we are trading off the bandwidth. Okay. You see the frequency response corresponding to the solid curve was flat up to P1, while now we are basically cutting off all the frequency above PD. Okay, so we have indeed a narrow banding effect. So even when put in the feedback loop, we have this new omega null, which is much smaller than the original one. But nevertheless, this situation is most favorable in terms of stability. Okay, so stability is typically a mandatory request for our circuit. So that's the reason why it's even more important with respect to having a very large band. Okay, so this compensation behavior strategy is called a frequency compensation with dominant pole. In the next class, we will see some alternatives, and then how to implement this compensation concept in practice in our circuit. Okay, thank you very much for your attention, and have a nice weekend.
Goodbye, Professor.
Bye-bye.